Hi, welcome to Earth Science with Mrs. Miller. Hi, welcome to Earth Science with Mrs. Miller. We're looking at Chapter 10, Plate Tectonics. Now, 10.1 happens to be continental drift. What we're looking at or trying to accomplish with section 10.1 is to be able to describe the hypothesis of continental drift and identify the evidence supporting continental drift. Now, some of the vocabulary that I want you to be on the lookout for as we go through the section is continental drift and Pangea. So the question is, why is continental drift important? Well, basically, that theory led to the theory of plate tectonics, and that describes many of the Earth's processes. So, first we have to understand the idea of what a continental plate is. Now, the continental plate theory is a theory that the Earth's crust is broken up into pieces and floating on top of a molten lava-like layer of material. So if we call this red section lava, this is the upper crust. And as you see, they're broken up sort of like pieces on a puzzle or pieces of a plate broken up. And they can slide and move around on each other, and they can hit each other, and they really don't have any fluctuation of movement except within that space allowed. So now as we go through this, I want you to keep that idea in thought. Now, continental drift. Originally, Abraham Ortelius, who was a Dutch map maker, noticed that South America and Africa actually sort of fit together like a puzzle. Now, along comes Alfred Wagner. Now, he was a meteorologist. Now, what's a meteorologist? It's somebody that studies the stars. And in a 1912 lecture, he presented his theory of continental drift. Now, he said that the continents originally were one large landmass that he called Pangea, and he said that they moved away from each other to their present locations. Now, Pangea means all land. And this idea wasn't really accepted until after his death in the 1930s. Now, he proposed that the continents plowed through the ocean. And now, this would cause a lot of disagreement, and the continental drift theory didn't explain everything that was on there. Now, we have some more evidence that was presented later after Wagner's death that we're going to look at. So those pieces of evidence, we have some fossil clues. We have Mesosaurus, which is a swimming reptile. So Mesosaurus is a swimming reptile, and it's found in South America and Africa. Now, it is a swimming reptile, except it's a freshwater swimming reptile, and there's no way it could have made the swim from South America to Africa with their continents and their present-day location. Now, another clue is these plant clues. Now, Glossopteris is a temperate climate plant with evidence found in Africa, Australia, India, South America, and Antarctica. Now, Australia, India, South America, yeah, okay, we could have some temperate climates going on. Africa and Antarctica, not really. So we got some extreme environments, two very extreme environments going in there. But still, Glossopteris is found in all those continents. Now we have climate clues. Spitsbergen is an island in the Arctic Sea, and it has evidence of temperate climate. Now, Arctic Sea is pretty cold. Not finding temperate climate there right now. Now we also have South America and India with glacier evidence. Now what do I mean by glacier evidence? What I mean by that is that you're finding deposits. When glaciers come down and they are ripping away sediment and everything, they're going to deposit it someplace else. Right? Now, South America, India, Australia, and Africa have large land masses that originally once were pulled together in the southern region. Now, our final piece of evidence that we're going to be looking at is the rock evidence. Now, the Appalachian Mountain chain found in the northeastern United States, Pennsylvania, Kentucky, Maryland, New York, and on up, is a mountain chain. The Appalachian Mountain chain is very large, Appalachian Trail and everything. Most of you have heard this. Well, it is a continuation, that mountain range is a continuation of the eastern Greenland mountain range and a mountain range that's found in Europe. Same type of rocks, same dating. Actually, it appears, if you would put it together, that they would be one mountain chain. And as you can tell from this nice picture, it actually looks like we could slide them right in together, and they would just continue on. So, Wagner's continental drift hypothesis in a nutshell. Continents fit together like a puzzle. The evidence supporting the hypothesis is that the organisms on multiple continents were separated by large oceans and couldn't have crossed there on their own. We also have geological evidence that those mountain ranges that we were talking about, that extending over multiple continents. And we have climate evidence, glacier evidence in areas that are tropical, and we also have the evidence in Spitzenbergers on the temperate climate. So, how would these continents have drifted? Now, physicists out of hand already rejected Wagner's idea that the continents plowed through those oceans, and they had no other theory of how the continents would move. So it sort of fell flat. But in section 2, we're going to discuss something called seaboard spreading, and how that discovery led to an understanding of how the continents moved. Now, here's a good time. We're going to take a break. We need to write down the listening check and write the answers in your journals. We want to know how Wagner's ideas originally were rejected, or why, how he used climate clues to support it, and those rock clues, as well as the fossil clues. And we want to know what you would expect to find, why you would expect to find similar rock structures on continents that were once connected. Okay, this is the end of section 10.1. We'll see you later with 10.2.